record on this computer. Okay. Oh, I'm right. So because it came up during in the chat on Discord, let me go ahead and check. So final exams. This is how I figure out where the final exams are. Let's see. So first off, I know it's a 4-hour course, but if it was a normal class, and we're not a normal class, but for normal class, because it's a 1 lab hour course and 3 lectures, you'd be looking over here for the time, which is not where you're actually going to find our time. So because you might look and say, 11 to 12:20, that well, that doesn't work for us, right? And you'll find none of these times work. So we scroll down and we look and we see over here on common finals that we have that if you look for 2168, CIS 2168 are 4:30 Friday at 3:30 in the afternoon. So rather reasonable time. I don't remember when it is until I don't really care until like a couple days from now, but we'll have our, see, is it really 4:30? Okay, how many more weeks do we have? Okay,
I think it's next Friday.
Yeah, next Friday. Okay, yeah. So for some reason I thought, okay, yeah. By the way, Doom is here, right? It's our last actual week. So so I will be doing, well, then we have the hanging Monday, so you get to hang out with me for one more day and we'll figure out what we're going to do that day. But let's see, I might run out of good problems by then, because if I go over all the problems, then I can't, there's only so many problems I can put on a final. Okay, so let's go ahead and see here. All right. All right, suppose you have, let's go and look at problem 3. This is a scenario. So, and I barely remember this one, so this is a good idea to look at this one. So suppose you have a set of instructions where you look over some time period to do, where over some time period, you do a constant number of insertions, so constant inserts, and a linear number of lookups of the maximum. To maintain your set of numbers, you can choose either between a heap or a binary search tree. So we are inserting, so we're comparing and contrasting a heap versus a binary tree, okay? So we are inserting a constant number of times. So the insertion cost we can ignore. So all we're comparing is the lookup time. Assuming you're interested in minimizing the average total runtime over the time period. For each structure, what is the asymptotic upper bound of the average runtime case? And which of those 2 structures should you choose? So, so we ignored the construction time because it's saying, hey, we have a constant. So like we're inserting 1,000 items, but then there's a linear number of lookups of the maximum. So, and that's the key of the maximum. So in a heap, you can just, okay. So in a heap, average amount of average time complexity, find the biggest item in a heap. Well, assuming it's a max heap, it's going to take constant time, right? To find the top item. If I'm just peeking. However, it's a right. So if they're saying, hey, you can choose between a heap. Yeah, we should. I mean, no, you can. I wouldn't assume anything for the heap. I would write down your assumption if you've got a heap, because a min heap and a max heap may have special. They differ. But for insertion, but doing it when sorting, you can assume it's a max heap. Okay, so you can choose either a heap or a binary search tree. So if we're finding the maximum item in a binary search tree, that's always going to be on average. So here we're assuming average case scenario for the binary search tree. Okay. So here we've got average case, worst case. So let's go with the tree. We're more familiar with that one. If we're looking up something, the biggest item in a search tree, right? That is going to be the item all the way to the right, which in a balanced tree, which is the average case, we assume that's log n. So it would be n log n because we have a linear number of lookups log n. Okay. Now, let's go ahead and take a look at the heap. I don't know if this problem is really being described, if what the assumptions are being really carried across into this practice exam. So I'm talking with the best I can. Now, suppose you're interested in the worst case. For a binary search tree, again, worst case scenario is that giant diagonal linked list or something that just goes zip, 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 zip back and forth. So still, we're looking for the rightmost one. So on a binary search tree, worst case scenario is that's all the way to right. And it's at the end of essentially a linked list, so it would take O of n time to find. So that would be n squared over the entire lifetime of that, since we're doing n lookups. Yeah, no. Okay, where's the max min heap? And if we're looking for a max heap and we're just looking for the maximum item a bunch of times and not actually remove it, it's constant time in both cases for lookups. So it'd be O of n for if we're doing it n times. I feel like the question could be better written, but I don't. But it might be appropriate for what their class is talking about. Let's go ahead and take a look at hash tables. Hash tables are very common in practice when we have a lot of insertions, deletions, and search operations. So we're under the assumption that we've seen under the assumption of uniform hashing, which is basically assuming that if you've got a hash function, if you've got a magic hash function, h of x, and you're given, or h of k, and you're given a key, right? We have basically the ability to if we've got basically this magic hash function, it's going to uniformly distribute things as opposed to my terrible hash function, like all hash things hashed to 0. We assume that it's uniform and at random. This is actually a terrible assumption, and it was actually part of my dissertation, which is that a lot of data structures will assume, and distributed hash tables assume you're going to be using a lot of schemes assume uniform distribution, but then the hash function they describe isn't actually uniform, such as a cryptographic hash function isn't actually statistically uniform. Which means that if you're getting large samples, you can get clumps, which, okay, that's fine, but you want it basically uniform. So it's saying that basically under the assumption of uniform hashing, collision resolution by chaining, so bucketing, chaining, and a constant time computable hash function, deletion, search are both 1 plus n divided by m over the average case. So I believe n would be the total numbers in there, and m is the number of slots we have. We can also see that this fact can be reduced to constant time under an additional assumption. Describe the additional assumption. So what gets this down to constant time? Anyone? Like, it's just ignore it. Well, let's go and look at the textbook. Because if you're looking for a specific answer, I am drawing a blank on it, even though I should know this. It's been that kind of semester. Yes, speak.
Would it be if the size of the array is infinite, then...
Oh, chaining. So...
like if m goes to infinity, then n over m would go to 0?
Using chaining, if an item is on the table, on average, we have to examine the table element corresponding to the item's hash code and then half the items in the list. The average number of the items in the list is L divided by 2. So it would be... So the assumption here is that basically that... Oh, right, assumption. If it's uniform, then the entire... All right, we can remove it with the... I would say that basically that the assumption here that reduces it to constant time is that is by replacing that with a load factor instead. And what I'm saying here is that, right, the number of comparisons we have to make if everything is uniformly distributed is 1 plus L over 2, right? one to actually get to your location, and then you have to look through half the items in the list. And load factor would be the average number of items per list. So that is so the number of comparisons that you have to do is on average 1 plus L, which is the load factor, over 2. The load factor here is the length of a list. An average number of items in the list. Actually, load factor is probably the term better applied for this. So L in this case is list length. Load factor is better applied for open addressing. If you've got the 3rd edition of the textbook, it would be page 341 that goes over this, but it's not super important for the exam. Anyway, suppose you've got some, this is the question I like and why I like this one. Suppose you have a hash table and have inserted some elements in it. When we expect it, we see that the result is as the pictures below. Being a good student, you realize this is a problem. So we have 3 questions. What is the problem? Give me a hash function that results in this problem. See what would be a better hash function, which is pretty much almost anything else. All right, so here's our table. Right, so this is hash function with chaining. L is length. L is length of the list. L in open addressing is load factor. So you're not wrong. It's L is less than the list in chaining, or average length of the list, I should say. So anyway, what is wrong with this this over here? What's wrong with our distribution of hash values?
They're all being mapped to the same place.
Okay, so we're all being mapped to the same place. So is there any pattern we can see? So, well, let's see. What are the gaps first off? Do we see that we have a lot of gaps? Do we have any idea what those gaps are? Like anything special about the gaps or patterns in them?
It's all like, it's 2, 4, 6, and then 10, 12. I don't know why there's some gaps, but it's at least even numbers where it's putting it, and a bunch of odd numbers where there's gaps.
Right. So we aren't using any even slots. So let's come up with so problem B is give an example of a hash function that would get us to this behavior. So let's see. Well, I generally find saying things out loud when a professor comes up with a puzzle, a silly puzzle like this helps. So index 0 gets 0 and 30. 2 gets 21, 31, and 1. 4 gets 2, 6 gets 33, 63. 10 gets 15, 12 gets 26, and 6. Anyone seeing a pattern now that I'm saying numbers out loud?
It's basing it off the digit in the ones place.
Yep. It's basing it off the digits in the one place. So or at least a possible solution. I'm sure that I guess it's theoretically possible that we could come up with another solution, is that that given a key K, we are equal to is equal to K mod 10, K mod 10, and then multiply by 2. And we don't need to mod anything else to keep it in the table, because mod 10 will keep it between 0 and times 2 keeps it in the range. So it looks like we get the ones place and multiply it by 2, right? Anything ending with 0 ends in spot 0, and anything ending in 1 gets into the 2, anything ending with 2 gets into 4, anything ending with 3 gets into 6, 5 gets into 10, and so on and so forth. All right, so now for the next question. which is, please give me a better hash function because this one is terrible. Which is why I said this answer for C was almost anything else. So what's a good one? Or what's a better one, right? We don't have to come up with a good one. We just need one that's better.
Could you just have it be the number itself and then as the function?
Well, what if I put in, well, then what would happen for 38 then?
Oh, I mean, wouldn't you mod by the array
Yeah.
list? Like, is that
Right.
part of the hash function itself, or is that a separate thing where you'd mod by the array list length?
I think in this problem, it's the assuming that we're modding it by there. In most exams, I see it as the assumption of the hash function.
All right, thank you.
So, I mean, I suppose you could debate it. I've never been really clear on that point. Because yeah, we could do h of k is k plus 1. And then, oh, that would leave 0 blank. But, and yeah, again, you want to mod that by 20. Normally, I would just simply go for something simple like take it and mod by 20. Or if we want to be really realistic, we can say mod by 19 because modding by prime numbers gives us a very, it reduces collisions because math. I'm tired today, really tired. Not that I'm ready for the semester to be over. I'm just been running back and forth and trying to get stuff done. But yeah, basically just saying, give me, if I go into it, I'd be basically wasting our time for this class, I feel. I want to, but I want to also do it justice, and I don't think I can do so in the review session. And again, I mean, that's stuff I'll reserve, that should be reserved for a higher level class. I'm interested in data structures, not on on the mathematics of prime numbers, right? So I'm staying in my own lane. All right, so let's see. All right, so problems 7 and 8 are tricky, are interesting ones, I think. So suppose we insert an element into a binary search tree that does not already contain X. So we have an item X. We have a binary search tree that does not have X. And then we've inserted it. Now suppose we immediately delete X from the tree. Will the new tree be identical to the original one? If yes, give an answer with no more than 3 sentences. If no, give a counterexample. Draw pictures if necessary. So what do people think about this one? To me, the answer, so this one is I think yeah. And George is completely correct under the assumption that we are working with a binary search tree that is not balancing itself, right? Our answer should be basically, if we're balancing, if we're balancing, all bets are off. Okay, right? If we're dealing with a self-balancing binary search tree, then all bets are off. But if we're dealing with something like, but if we're dealing with the binary search trees that we've been dealing with in class, and that's what I would expect us to do, then yeah, if we've got some tree over here, right? We've got a subtree and a subtree, right? And suppose now we're going to insert X, right? We're going to insert X somewhere. X could go there, or it could go here. It doesn't really matter, but it's going to be a leaf, right? Everybody understand? And now, suppose we want to delete X. To delete X, it's a tree. Sorry, to delete X in a tree, we find it, it's a leaf. And to delete a leaf, we just simply replace it with okay. We delete it with null. Sorry, replace it with null. And so this basically goes away. All right. So yeah, if we're just adding something to a tree and immediately deleting it, we're adding a leaf, deleting a leaf, it's gone. Boom. Okay. I'm sure you could probably draw a more elegant flow chart than I could. And also we, again, another key thing there was is that the tree does not already contain X. If it already contained X, right, that's another completely different solution, because if it already had X, right, then, and we allowed duplicates, right, if X was the root, why is my pen giving me so much trouble? I don't, okay. So if it already contains X, right, and then we add X to it, and then we try to delete X, we're going to basically try to delete this guy and grab its next in order successor, wherever that ends up being, which would probably be X again. So, but it might not be, depends. Anyway, more examination needed on that. But problem 8, so now the same thing for something for a heap. Suppose we have a heap and two values, V1 and V2, such that all values are distinct. Let heap H1 be H12 be the heap if you insert V1 and then V2 into the heap, and 21 be the heap if you do V2 then V1 into heap. Give an example of heap V1 and V2 such that 1 2 is not equal to 2 3. No justification is not needed. Just draw the heaps H 1 2 and 2 1. Right. So here it's saying, hey, we've got some initial setup of a heap, right? And then we've got two items, V1 and V2. We can call them X and Y if we want to. And basically show that if we add them in different orders, we're going to get a different heap, right? So let's go ahead and just do 2, 4, 6, 8, 10. Let's do actually, let's do powers of 2, 2, 4, 8, 16, 32, 64. Okay. So now let's assume I want to add the number. So if I add the number, let's see. Let's just see what happens if I add numbers. So if I add 1. Okay, yeah, I think this might work actually. So if I add 1 over here, we get the bubbling action happen. So we'd get 1, 2, and then 8 over here. Right? And now if we add 3, let's see what happens. If we add 3 over here, we would basically bubble up again. So we'd have 16, 4, and then 3 over here. Okay. So 1, 3, 2, 4, 32. Okay. Makes sense to me. Now let's see what happens if we insert 3 first. So we already get a major difference, which is that 3 doesn't bubble up over here as much. 3 goes up, but it doesn't bubble up to 2. Then we add 1, and we can immediately see that that's a different thing, because we get 16, then 4, then 2, and then 1, and we'd get 1, 2, 3. Now, why did my first example work like that? Because powers of 2 give me a good amount of spacing. That's what so I thought, hey, let's try something with a good amount of spacing so I can choose a lot of numbers in the interval. You can't get it to stay? Bring it over here. Whoops. Yeah. Bring those pieces over here. Bring them over here. We've got a Duplo break, people. So a triangle on the bottom. Okay. And then you want this on the top like this? Oh, yeah, it's not sticking. That piece is like loose. Let's see. That is a problem. What if we swap them around? Sticks a bit better, but not really. Okay. All right, so Now, now when I did this, I was thinking I had two strategies here. First, when I was creating numbers, I went with powers of 2 because that would give me a lot of spacing between successive items. So, I mean, and if I had to fit multiple items in between 2 and 4, I could with, 3 and 3.5 or 2.5 and 3, right? Similar. And then by leaving one space open, I was like, I would have something over here. I wonder if that next space would be open. I wonder if that would affect it, which it did.
If you were to do it on where, let's say if you didn't have 64, so the two things you were adding would be in the same
It probably,
thingamajig.
I don't know. Does it give me different ones? I wouldn't know until I drew it. I'm gonna move on to the next problem. All right, because I like this one as well. Suppose you have a graph like the one below. The dot signifies some part of the graph you don't know exactly, not a straight link. In other words, we've got two nodes. We've got a start node and we've got an end node, which is a goal, but there's no direct link between them, right? You can't go from start to goal, there's no edge that connects start to goal directly. There's no, right? There's no one single step that gets us there. You do know that there are many paths from start to goal, right? You also know that they tend to be rather long. Suppose you want to implement a program that searches for a path and returns the first one it can find. You don't need to find the optimal path in any sense. Just any path would do. You don't need to find the optimal path in any sense. Just any path will do. Would you want to use breadth first search or depth first search for this program? Okay, so why DFS?
Because the first thing you'd want to do is see if you can get all the way to the end. So you'd want to be going deep before you go wide.
Good answer. Does anybody have an argument for breadth first search? Anyone have an argument against breadth first search? Because I can think of a good argument against breadth first search. BFS would give us the most optimal and it would take longer because if we're assuming that this network has basically all roads lead to Rome. In other words, we've got a source and a sink, as it's called. Basically, imagine like we're pouring a bunch of water from the top of the hill, and we're watching it go down, and they all go down into the same drainage area. Then that's then breadth first search and depth first search would be assured to go there. BFS would go through every single path to get there, which takes a while. Now it would give you the most optimal. Dijkstra's algorithm is just breadth first search, just a weird way of just a different way of doing it. Look it up on the Wikipedia page, but it kind of shows how to. The idea here is that you can kind of do breadth. You can kind of do here. It's a kind of weird way of doing it, but the way I've always kind of compared the two is that like if we're trying to find the shortest paths between places, right? This is equivalent. We can kind of mentally rewrite this as, so we've got a node here, we've got a node here, we've got a node here. Why am I filling them in? There's no need to fill them in. And that's kind of equivalent to them being the same as you've got a node here, and then you've got like a little node, a little node, and a little node. 1, 2, and a big node. If you kind of rewrite the graph like that, right? it's kind of it's going to essentially be the same thing. And so if I do another one over here, we can kind of figure that out. Basically, you can rewrite the graph and kind of get a breadth first search algorithm for it. Now, if you wanted to find the most optimal path, though, breadth first search would take a while. It would have to go over every kind of path. Now, one trick, though, that I do like for breadth first search, which I find very cool, okay, is that you can do I don't know what the name for it is, but you can basically do a two-sided breadth first search. So we can start looking breadth first search this way and look and travel through these, but then we can do breadth first search from here as well and just kind of swap them off. So we do one step from the start, one step from the goal, and then we do 2 steps from the start, then 2 steps from the goal, and we can kind of meet in the middle. And it actually ends up being much more efficient because you don't necessarily have to go as deep as you do into everything else. It's a pretty cool trick. Now, I'm going to go ahead and go over a coding problem now. Okay, so let's go ahead and figure this all. And unfortunately, you know, what I had here for was an exam in this page used to link to a final exam, but unfortunately it does not anymore. I don't know why, but it was a good exam. And the reason I liked it is that it was in C++, and so you were C++, and so you were able to see, oh, a lot of what I've learned over here is pretty compatible with other languages, right? So we just did the problem in Java anyway. But the idea here is that suppose we have a text file, and the text file is kind of formatted like this. Okay, so I like this because it's a file reading, and I love my file reading problems because it allows me to do arbitrarily large inputs. And we have a text file. Is what posted on Canvas. This PDF can be found on my GitHub page by going to Classroom. Then you can go to data structures, and then you can click on the study guide, and the front page has my GitHub link, so you can get into here. And it's probably not as good as a study guide as some of you may have made, but basically it's just simply the topics that I will be covering and what you should know. And also for the exam, you will not be writing any data structure. You will be writing code that uses them. Okay, so keep that in mind. All right, so anyway, let's get back to here. We have a file, and it's going to basically it's going to look like this. Okay, file has usernames and logins. Okay. Formatted username space seconds and login durations. So basically the file will be formatted with the username, the space. I don't think I put the Huffman encoding on the final exam. Username, a space, and then the second spent logged in. So we might see a file like this. Now that I've got this, the file might look like this. We're going to say Alice was logged in for 600 seconds. Bob was logged in for maybe that. Alice was logged in for 1200 seconds. Alice was logged in for 300 seconds. Carl was logged in for 10. Darla was logged in for Darla has logged in for a while. Alice, and let's just go ahead and say ... right at this point, right? So the file is always, here's the username, whatever that username is. I'm just using Alice and Bob and just names because that's easy. And then duration. So my question is twofold. My question is basically one question, which is I want you to calculate the average duration, the average session time for each user. So how long does each user typically spend logged in? So for instance, if we go through, and these are the only entries for Alice. Alice has spent 600 seconds, 1200 for 800 seconds, 2100 seconds total, divided by, so she's been logged in 3 times for 2100 seconds, divide by 3, that means she's logged in for 700 her average login time is 700 seconds. Make sense to everybody? So we're calculating the average login duration. Make sense?
Can we assume that there's no duplicate names?
You can always assume that the username, yeah, it's a reasonable assumption to say that the username is unique, because otherwise how would we know who's logging in?
Right, okay.
Calculate because we're dealing with a file and we're dealing with basically two things, and we're dealing with, trying to average things that we don't know in advance what they are. We don't know who all the users are. Then it makes sense that this is a map problem. So let's go ahead and do public static, and we'll do we can either return a hash table or we can just print it out afterwards. I'm going to print it out. Public static void average. You know what? I'll return the map because that will let me know what I want to do with it. And so we need to calculate for each user. So the username will be a string. That makes sense. Any name is going to be a string. And then we want the average duration for each person. So that's going to be a double, assuming I can spell it, which today seems to be an unreasonable assumption. Okay, map string to double and calc. So let's go with average login. For our input, since we're going to be reading a file, I'm just going to basically go with string file name. Okay, and then I'll handle the file reading. Okay, so and then we are going to have our map string comma double over here, and it needs to be, let's see, the average duration equals new hash map, and then we're going to just simply return that at the end. Okay, so to calculate the average, we need to know what two things. So to calculate the Alice's login time, what two things do we need to know about her, right?
How many times she logged on, and then the duration of each logon, I guess.
Yep. So we can do this by either creating one or two maps. We can either keep track of, basically store all of Alice's login. So basically make a list saying Alice logged in 600, 1200, and 300 times, and then basically average, sum and divide, sum up the list and divide by the length. Or we can sum up the list and count the number of times we see her. I'm going to go with that approach. So we're going to need to do the average later. So I'm just going to move it down here so it doesn't get up. But basically, this was one of the givens for the problem. And this was one of the givens for the problem. So string integer num logins is equal to new hash map. And then okay, so we have basically each person was logged in for a certain a certain number of times, and then we also keep track of how many, and we keep track of their total time logged. It's not the only way we could do it, right? We could do it with a string and a list of integers, but it seems more appropriate to do it this way. And this was the way that the problem was initially formulated. So what we're going to do now is that we need to read that file. So scanner. Let's go ahead and do that. And now fix that, import that is equal to new scanner. And then I'm just going to read in the file name, boom. And it's going to yell at me because new scan. Oh, right. No. New scanner, new file. Now it's got to yell at me. Amazing how basically the fact that I didn't get an error let me know that that what I wrote wasn't going to work. Isn't that funny? All right, so now it says surround with a try with resources block. Try and do that. And you know what? I think I'm going to go ahead and be lazy here. And what I'm going to do is I'm going to first off import java.io.file. So that will go away. But then we've got this error with scanner and it wants me to try it. But all I'm going to say is just basically I'm just going to throws exception because I don't want to deal with a try catch block and it's going to look messy otherwise. Oh, I'm going to say throws file not found exception. There we go. Because that's more explicit about what's going to happen. Because that's what could possibly go wrong here. File not found exception. So while scanner dot has next, and since this is basically all this stuff is line by line, I'm just going to do a read line. So string while scanner dot has next line, scanner dot read line. Always easier to try to read everything one line at a time. String line is equal to scanner dot next line. There we go. So while it has next line, read the next line. So we've got a line and its line is going to have basically number space 1200. Okay, what do we do with it now? Fairly straightforward. We just simply split it and say array. Sorry, we say string array parts is equal to line dot split. Sorry, just thinking I've been doing this kind of stuff so much in Python that I'm having to switch gears mentally. So we're going to split on our space. It's only they explicitly said it's going to be a single space, so I don't need to write a regular expression or anything for that split. Split takes in a regex, by the way, just natively. Very good to know. So string parts line dot split. So we've got two parts. We've got our username in index 0. And then we've got our duration in index 2. So let's go ahead and just, even though it's unnecessary to write these out individually, it's just so much easier to read if I simply say string username is equal to parts 0 and int duration is equal to integer dot parseInt, and I'm assuming integers. I think that's a reasonable assumption. And if not, it's literally just changing one data type, replacing all instances of integer with double and all ints with double. So it's such a silly little thing that doesn't really matter. Integer parseInt, and we're going to simply say parts 0, 1 because again, it's a string, so we have to convert it into an integer to actually use it. So we've got a string, we've got our number, and so now we can, now that we've have read it, okay, we can basically, so read line and get parts. And now we can say, now we can add to map. So one of the things is that basically these lists are the data in these lists, sorry, in these maps are dependent on each other. So checking one is essentially going to work for checking both. So what I'm going to do and basically say, hey, if, and they both have the same keys. So if num login that contains key, it already kind of knew what I wanted to do. So if we haven't seen this username before, so if we haven't seen the username before, we're going to do one thing. Otherwise, we're going to do something else. So let's go ahead and look at that. If we haven't seen it before, then okay, then the total times, then the number of times that this person has logged in dot put is going to be 1, is going to be username has logged in once, right? So if we haven't seen them before, then, well, we've seen them once now. And also the total timed log, well, the total number of time they've been logged in is the time we just read. Oh, and I should just remember to actually complete what my sentence is, so to speak. Okay. Otherwise, I have seen them before, so I just need to retrieve those times. So num login dot put should be replaced with num login dot what am I doing? I tried being smart and ended up doing just as much work. All right. So what do? I say, hey, I want to replace. So if I have seen them before, I want to replace the number of times I've seen them, the number of times I've seen this person with the number of times I've seen him, but add 1 to that number. You can split it up into 2 sentences if you want, or 2 statements, but why? Because it's easy to read, I'm sure. And then otherwise, we need to do the same thing over here. Total time logged is equal to put, and rather than putting in the duration, we are going to do the same thing over here, which is we are going to put in the amount of time that they've been here, get the number of time they've been here plus the amount of time they've been here for. Okay, so we've added it all to the maps. Excellent. Are we done yet? No, that was just the file reading. Part of the reason why I like this one, it was that it was a weighty problem and it tested a lot of things. So we put it in and now we have to compute the average, which basically involves us needing to iterate over our hash map. So for each, and what I'm going to do is I'm going to say for every string username, it doesn't matter which one I use, but for every string username in total time logged dot key set. So for every key, so for every username, I'm going to go through and basically I'm going to figure it out. And I can, again, do this in one line, which is going to look awful, but hey, average dot put. So for every username, I want to calculate the average. So average dot put the username, their average is going to be what? Their average is going to be, well, the total amount of time they logged in. So total time logged dot get username divided by let's see, sorry, I was just thinking ahead. Num logins dot get username. So the number of times, so the total amount of time they've logged in divided by the number of times logged in. Of course, we get an error here, which is going to say what's going on? Cast second parameter double, right? You can't turn this into averages are, you need, when we're dividing, we kind of need an average and normal. So here's the thing, right? Ints and doubles, they can interact just fine. Let me go ahead and pull up the terminal over here. So J shell double D is equal to 3. No problem there. It converts it into that, no problem. Double capital D, right, is equal to 3. We get an error, right? It will automatically convert between primitives, but it's not, and it's automatically going to auto box things of the same type. So your ints into integers, your doubles into doubles, your chars into characters. But when it's a matter of like converting one object to another, it isn't going to do that. Or so that's why we're getting an error there. Also, you know, when you're dividing, you kind of want to know on it. The decimals are kind of useful. So we could do a convert, we could like throw it in, but again, we'd get a double value. So what I find to be easier is just to do this. 1.0 times that value. That way the entire thing's actually calculated as a double value. And then we're done. So we needed only 2 more lines. We needed the for loop and this big monstrosity of a math statement, but hey, it's done now. Pretty good, right? I like that problem a lot. All right. Now let's go over, now let's step back into some theory stuff. Things that are going to, so this page is definitely going to be very similar to what's on the exam. Not this one over here. This one, question 2. In this course, we've seen many different data structures. And I was, you know, I'm just glad that other people do these questions too. Here's the following: list, either a linked list or array list, a 2D or higher array, a stack or a queue, a hash table, tree, binary search tree, undirected graph, directed acyclic graph. So what is that term, directed acyclic graph? Anybody want to take a crack at it? I believe I went over it in the videos. It is a directed, well, tells you what it is. A directed graph with no cycles. Where have we seen these? Right? Directed acyclic graph. Cyclic means has cycles. Acyclic, no cycles. So where have we seen a directed acyclic graph before? Yep, topological sort. In order for things to be topologically sorted, you need directed acyclic graphs. Directed acyclic graphs kind of are a memory. Not necessarily a fond one for me because my qualifying exam was all about those things. So that was fun. So anyway, so for each of the data following applications, tell me which of these data structures would be the most suitable and give a brief justification of your choice. For data structures like trees and graphs, describe what the vertices and edges represent. And if they're weighted, describe what the weights are. So this is from University of Washington. So let's see. Map of the Puget Sound highway system used to display travel times on a web page. The map displays principal cities, intersections, and major landmarks, the roads that connect them, and the travel times between them along these roads. Travel times along the same road may be different in different directions. So what kind of graph is so, well, this is a graph, right? Why is this a graph? So anything. So first off, when we're talking about maps, that should be basically a kind of a idea that this is a graph. Anything that you're dealing with a map generally gets reduced to graphs. In fact, maps are generally like the quintessential kind of like the quintessential example of applications for graphs. But although I disagree mildly and think that social networks are basically kind of make better graphs these days, for examples. But let's go ahead and see. So we've got, so if it's a graph, first off, is it an undirected graph, a directed graph, or a directed acyclic graph? Anyone? Yep, it is a directed graph. And the key there is that travel times along the same road may be different in different directions. So what are the nodes, what are the edges, and what are the weights? Weights are the travel time, yep. And the nodes are the cities or other landmarks. So basically anything that you want to travel to and from, those are that. The relationship is I can get from here to there. That's the edge. So the edge is the roads. Very good. Oh, I wonder what you would use for this. An 8x8 chessboard. What data structure could you possibly use for this? If only there were an assignment I'd given. Yeah, 2D array. We use that one, right? An 8x8 chessboard. There's no need to go be any more advanced than 2D array for it. All right. A computer model showing the dependencies between the steps needed to assemble a B-787 airplane at Boeing's Everett plant. So what data structure is this? A linked list. Well, not necessarily, because Jacob's got it, a directed acyclic graph. Anything where that the keyword here that should set you off is dependencies. Because when you've got a complicated when you've got a complicated kind of thing that's multifaceted, right? You might need to build this part, which requires you to build this part and this part first, which then and this part requires these two parts, which require, and this one just requires this part and this part and this part. And by the way, all of these parts are reliant on this single doohickey over here, right? So basically these can all be kind of done in, you can kind of choose which outer onion you want to work on first, or you can have a team working on this one and then a team working on this one over here. I really don't know why it won't write. Do I need a new nub for it? But the point being is that basically anything that basically is a dependency graph is a anything that uses a dependency graph basically is a directed acyclic graph. In fact, this kind of thing is graph theory is kind of how GitHub works. Much better. Okay. A legal list of words in Scrabble. We want to be able to quickly check whether words used by players do in fact exist in the list of legal words. So what data structures would we use here? We've got this list of words in a Scrabble game. We want to quickly, yes, a set. Yeah, the list here is a crimson colored fish, a red herring, if you will. So the idea here is that we've got a We want to check if something's a valid word. You want to set. We want to see, is it there? Sets kind of, you get true or false in a constant amount of time. Description of inheritance relationships between classes and interfaces in a Java program. Now, you might think this one might be a graph because, again, you've got dependencies, but with the way Java works, well, let's see. Yeah, because it's a hierarchy. Because it's a tree, because you can basically pick up one node and everything is going to dangle from it. All right. A history list that records sites visited by the user of a browser. As new sites are added to the list, they are added to the list. So the operation also supports the operation of going back to the web page that was previously visited before the current page and going forward to the next page visited. So if this was the only thing there, if you couldn't go forward to basic, so suppose we were just implementing the back button in a web browser, forget about the forward button. What would we be implementing? What would we be using? What data structure? Stack is correct, right? Because you can use that to backtrack. Now, if we wanted to go forward as well, I could actually use a second stack over here and basically say, hey, if I pop off by pressing on the back button, it goes into the forward. I push it into the front button. And that would basically, and then that would be an easy way to kind of traverse between them. Otherwise, another way of doing that is to implement that is to use a linked list and simply you would just, if you're going to a new page, you add a new node to the linked list and add it on to the end. And then if you go back, you're just simply moving where you are in the list. So there's a bunch of different answers for this one. All right. The nodes in an integer binary tree can be represented by the following data structure. Here's a binary tree node, has an item, a left and right. Complete the definition of a method of a breadth first search to perform a breadth first search of a binary tree and print out the node values in the order they are reached during the search. In other words, level order traversal. You can use and create whatever other data structures you need. I will do that. Thank you. So we're going to program a breadth first search. Now, because of the tree, your instinct is to create a because this is a you see the tree, your instinct is to write this recursively. That instinct would be wrong because breadth first search does not rely off the stacks, it relies off a queue, which is what we're really going to need here. So we've got a root. And then what are we supposed to return? Breadth first traversal of the binary tree with root R and print them out in the order they appear. It's a string. So we don't need actually, so it's just gonna be static void create breadth first search root node E public static E. There we go. We've got a node that contains anything we kind of want it to. And now what do we do with it? Yep, we make a queue. We don't even need to keep track of what we visited and what we haven't, by the way, because it's going to be because we aren't going to have any nodes that backtrack on themselves. All the nodes always point to their children. So, and remember, the way to pronounce a queue properly is to just say the first letter and ignore all the other ones. QQ is equal to new. And it's an interface, so I got to put in a linked list. It's going to be a queue of nodes of type E. Okay. Now what we do is simply say root, and now we're just going to simply add this root node to the queue. Queue.add root. Wow. The queue is empty. Q dot is empty is not true. So while the Q is not empty, what are we going to do? We are going to get our current node that we're working on, node E current is equal to Q dot poll to get it out. So we get the current item out of the queue. DQ. I don't know why they use poll and that the terminology. Never really liked it, but I mean, when you write the data structure, you get to when you write a program, you get to call it whatever you want. So we've got a current, got Q poll. Okay. Because remove, let's see, what does remove do? I think you can, they just have different kind of, they have different responses, whether or not something is null or not. So you could use remove. They act differently, I think, based off of whether or not the list is empty. So node current is equal to Q dot poll. And now what we do is that basically, let's go ahead and print it out. String, sorry, sout Q dot item. No, not Q dot item. Current dot item. So let's print out the contents of that node. Okay, so we visited that node, and now we just need to add its children, which is that. And so we can either, so we can have two things. We can either add nulls to the queue, or we can, yeah, it doesn't make sense to do that. I mean, you could, it's just it's not as intuitive, even though I like it more. So if current dot left equals null. So if we have a left node, so if current dot left is not null, Q dot offer current dot left. So if I have a left child, put it into the queue. And then do the same thing for the right, And keep doing that and until you're done. And then that's all we need. Questions on this one? Whew. Man, I don't know why I started yawning so much.
Would depth for search be the same thing except you use a stack? Or is the depth for search like just one of the traversals? Like would it be?
Is it? I mean, post order, it would be. It would be. Annie, can you come here and check on laser? Or it would work. I think it would be. I'm just trying to think. I think it would be post order traversal. I think that for search would just simply be post order traversal.
Would it be? Because when you do depth for search, like if you're doing it in a tree, would you do the root first, or would it be?
I mean, you'd put in the root, but then the root would be in the stack, but then you'd go down to the next one, and then the next one, and next one until you could go down no longer.
Mm-hmm.
All right. So it is currently 12:15, so I think we're good for the day. So, so on the next, so in the next couple, so on Thursday, I'm going to go over some graph problem, some actual like graph theory questions and some sorting theory questions. All right.
Rosen,
Yes.
can you upload the YouTube videos?
Oh, have I not? Okay,
No.
yeah, I'll do that.
Okay, thanks.
Right.
Okay, and we have class on Wednesday.
Yes, we do. All right.
Okay.
Take care.
Yep. Thank you.
Thank you.
See you.